And what's the other thing I always forget to do? Share content, right? There we go.
Always is it's pretty inclusive. I would say just sometimes.
Just sometimes. Well, that's
Just
right. I got you guys to remind me if I get out of line here. You know, somebody will tell me that I need to do this. All right, that's good. So we'll go over there, and you guys don't want to see my redox balancing notes because you guys have already done all that junk. So we're going to get us a new screen here. What do I call this? Usually quant notes, that's what I call it, in case I ever have to go back to it. What's today? The Ides of March, right? Beware of the Ides of March. Isn't this the Ides of March?
The 15th?
Yeah, come on, Shakespeareans.
Oh, I don't do English.
Or was that Julius Caesar? Beware of the Ides of March. Et tu, Brute? All that good stuff?
Nope.
Nope.
Can't.
Just not happening. All right. Okay, guys, looks like I got 3:30, so we can go ahead and get started. Now, hopefully everybody got my emails. I think I ended up sending a total of 2. So you know what to expect for tomorrow in lab and what's coming in, right? So just a real quick recap of that. The gravimetric analysis lab is due tomorrow, and I did send the emails to remind you how to calculate the mass of the precipitate, right? For each trial, it's final weighing minus final weighing. And then on top of that, so that lab's due tomorrow. I think I asked you guys to work up a calculation of the molarity of the NaOH based on your standardization trials you guys did last week. So that way I can kind of just see where you are. So I'll probably have like a piece of paper up there, and then you guys can come up and just write down whatever your average molarities are. I don't even need to know your name. I just kind of want to see, you know, how much variance there is in the values. And then the other thing was breaking up the lab into 2 groups this week and next week. So I think I sent you guys out a list of who's doing the pH meter titration tomorrow and who's doing indicator. Then you're going to swap in the week after that. So any questions about any of that? Okay, so I think that was all fairly straightforward. So you kind of know what's going on. So you have a quiz tomorrow when you come in. No homework. Homework is due in a week, I believe. And you guys do have that posted homework assignment. And I think as of today, you'll have all the information that you need to finish that assignment. All right, so let's pick up where we left off last time in class. And we were dealing with weak acid, weak base dissociations, if I remember correctly. And I believe we finished with an example of a weak acid dissociation. Am I right about that?
Yep.
Excellent, because I know you guys all go back and review your notes on a daily basis. All right, so anybody could have just jabbed that out there and said, yeah, that's exactly where you ended. So let's do a weak base. All right, so I picked a weak base. And like I said, I think I gave you guys all of these example problems in a handout, but I'm just going to sort of restate them. So let's say I've got a weak base and it's a 1.263 molar solution of methylamine. And you can go look up the formula of methylamine, but it's CH3 NH2. Okay, so you'll look at it and say, oh yeah, that's an amine base. It's got an NH something on it. So yeah, you recognize it as, oh yeah, that nitrogen has that lone pair of electrons. So it could accept a proton from an acid, right? So that tells us we're probably dealing with a weak base. Now, the other thing you can do is say, okay, if this is going to be a weak base reaction, I need a KB, right? But what happens when you go to the tables in Harris to find a KB? What ends up happening?
Only KAs.
Yeah, you won't find it. You just find the Ka. So you need to find a Ka for this thing, but what would be the formula of the thing you're looking up the Ka for? What would it be? What's the formula of the thing you're looking up the Ka for?
Wouldn't it be HCHNH2?
Yeah, you could write it that way, but I think the way the book writes, so it could be this. And of course, it would take a positive charge because the original base is neutral. Or it might show up this way. Probably in your textbook, it shows up this way. Okay, so that's called methylammonium. And it would be an ion. Okay, so that's how you would actually find it in the Ka table. So what is that? Well, it's the conjugate acid of the original base, right? So we could actually put that, it's the conjugate acid of CH3NH2. Okay, so we got a conjugate acid base pair there. All right, so I actually went and looked that up. And let's see, you guys could verify this for me if you want to, but as it turns out, the Ka for the methylammonium is 2.26 times 10 to the minus 11th. Okay, so that tells me that's not a very strong acid, is it? Not a very strong acid. All right, so now we might as well go ahead and calculate a Kb because we're going to need it, right? So remember, we have this equation we can use. We know that Ka times Kb is equal to Kw. Got to know what Kw is. That's 1.0 times 10 to the minus 14th, right? So now I can solve for the Kb since I'm talking about a weak base. So that's going to be the Ka divided by, or sorry, the Kw divided by the Ka that I looked up. All right, and what I say that Ka was, it was 2.26 times 10 to the minus 11th. And when you work that out, that turns out to be 4.4 times 10 to the minus 4th. Okay, so I got a value of my Kb for my original base now. Okay, so that's now 4 CH3 NH2. All right, so now we've pretty much got everything we need to go ahead and set the problem up. I got a Kb. All I need now is a dissociation reaction. Okay, so I want to know what the pH of this solution is going to be. So let's go ahead and pose that question. pH is equal to what? Okay, so how do I do this? Well, I need to show the weak base dissociating in water, right? So we have to go back and remember what a Kb reaction looks like. So for our weak base, it would look something like this. That's an NH2. What's it reacting with, by the way? If we're talking about Kb reaction, what's my other reactant?
Water.
Water. Very good. Okay, double arrow, since this is going to be dictated by Kb. Okay, so if the CH3NH2 is the base, what's water got to be?
The acid.
Yeah, it's the acid. Okay, so what happens? The acid donates the proton to the base. So you know what we're going to make? We're going to make the conjugate acid. That's the methylammonium that we were talking about just above. And what's the other thing we're going to get?
Hydroxide.
Hydroxide. Very good. Okay, so now I've got a conjugate acid and a conjugate base. Okay, so now I can go ahead and set up an ice table, can't I? So remember, this isn't a strong base dissociating. This is a weak base dissociating. So we got to use equilibrium techniques now. So I'm going to make an ice table. Now, do I have an original concentration of the methylamine? Yes, I do. It's the 1.263 molar. Okay, what do we do with water?
Cross it out.
Cross it out. Yeah. And we know why, right? It doesn't show up in the law of mass action. All right, so what values do I put in for the two products? Do you have any of them to start with?
No, this would be 0.
No. So we're going to put a 0 and a 0 there. Okay. All right, so which way does the reaction have to go?
Has to go to the right.
It has to go to the right. Can it go to the left? No, I don't have anything over on the product side, so there's no way it can go to the left. So I need to let the reaction go right to get to equilibrium. Okay, so I'm going to have a minus X there for the base. I'll have an X for the conjugate acid and an X for the conjugate base. Add down. And we get an X and an X. Okay, so now all this goes back into the law of mass action. So let's remind ourselves of what that is. So this is a KB. So it's products over reactants, right? So it's concentration at equilibrium of the CH3 and H3 plus times the hydroxide ion, all divided by the CH3 and H2. Water does not show up because remember, it is a pure liquid and a solvent. Now, what is my KB equal to? Oh yeah, we got a KB up there. It's the 4.4 times 10 to the minus fourth that we solved for. Okay, so now what do? Well, we plug our X's from the E line down into the law of mass action, right? So that gives me an X times an X, which is an X squared, all over 1.263 minus X. And that's going to equal to my KB, which is 4.4 times 10 to the minus fourth. Okay, so now you have some options, right? You want to solve for X. Now, by the way, what does X get you? X gets you the equilibrium concentration of hydroxide ion. Once I have that, can I get back to a pH?
Yep.
Yep, sure can. There's a couple ways I could do it. Okay, but sure, I can easily get back to a pH from there. So one way you could solve this is with the quadratic equation, right? So you could go ahead and quadratic it out and get your two roots and figure out which one fits. What's the other way I could potentially do this?
Since,
You can cross out the single X.
Right, I might be able to get rid of the subtracted X. So what's the assumption I'm making here to make that valid?
since you have a small KB, like it really wouldn't show up, so you can just toss it.
Yeah, pretty much. So I have a very small KB. So the two things I'm comparing are the value of the KB to the value of what I'm subtracting X from, right? If I have a small value of KB, that tells me that X is probably going to be small because the reaction can't go very far to the right, right? Because a small value of KB means that I'm favoring reactant heavily over product. So that tells me that X ought to be small, okay? But what I want to assume here to make this happen is that X is going to be negligible when compared to the 1.263 that I'm subtracting it from. Now, obviously, I can't get rid of the X on the top because that's a squared X, right? That's a multiplicative X. That's X times X. Okay, it's only additive or subtracted X's I can get rid of in a case like this. So what I can do, and we'll check it here in just a little bit, I'll show you the check that we do, is I can go ahead and now solve this thing. So X squared is going to equal to 1.263 times 4.4 times 10 to the minus fourth. Okay, now I'll see if I actually have that. That's 5.59 times 10 to the minus fourth. Now what do? Well, I take the square root of both sides, right? So my X turns out to be the square root of that, which turns out to be 0.024 molar. And remember, that's my equilibrium concentration of hydroxide ion. Now, here's what we would do. I don't think I told you guys this last time, but you'll use this also in dynamics. When you make this kind of assumption, you can apply this thing called the 5% rule. You guys ever heard of that before?
Yep.
Well, well, now you have. All right. So what the 5% rule says is to neglect an additive or subtractive X.
Dr. Richardson, I have a quick question when you're done.
Yeah, let me just write it out and then I'll let you go. here's the rule. X, as we calculate it, must be less than 5% of the value we're comparing it to, which in this case would be the 1.263. Okay, and we'll do that. But yeah, let's go ahead and take the question next.
So up top, whenever you multiplied 1.263 by 4.4 times 10 to the negative fourth, I got something different.
Anybody else want to try that? I mean, that looks about right. 1.2 times 4.4 should give me something a little bit bigger than 4.4. So I mean, it
just
looks
got
about
5.6 or 5.56 is what I got.
close enough.
Yeah, I got 5.56 too.
Okay, does that change the value of X? What should that be?
No, it stays the same at 0.04.
Okay, we're good then. All right. So let's check it. So what am I going to do? I'm going to take 5% of 1.263. So that's what, 0.05? You guys got the calculators there, so you guys can check me here. What does that turn out to be?
I got 0.06315.
Okay, so about 0.063. Okay, is 0.024 less than, equal to, or greater than that?
Less than.
So that's a check. Okay, so that's what the 5% rule says. Okay, now if it turns out that that value, that my value of X is greater than 0.05 times whatever number we're comparing it to, then that means that I would have to probably go back and do this using the full-blown quadratic method. Okay, but in most cases, when you're dealing with these really small values of K, you're going to be able to get away with this. But if you're not sure, run that 5% rule check and see. Okay, does the 5% rule make sense?
Yeah.
Okay, and again, it's just a real quick and dirty way for me to see whether or not that assumption about X being small is actually good enough. Okay. All right, so now I'm asking for a pH. So what do you think the next step would be? I've got my value of X, which turns out to be the hydroxide ion concentration. How might I proceed from here to get a pH?
Find pOH.
Okay, let's do that. So the pOH is the negative log of the OH, right? So that's the negative log of the value I've got, which is 0.024. All right. And what do you get?
$1.62. Well, 6.3 rounding, because that's our sig fig.
Okay, yep, sure is.
6.3.
So you get about 1.63, and that seems about right. Okay, so how do I get a pH from here? If I got a pOH, how do I get to a pH? Anybody remember?
You would take your pH in.
Anybody remember this relationship?
14. Okay, yeah.
That one, yeah. So given that we chose to run from the point of view of a pOH, that's what we do. So now we just solve for pH. So it's just going to be 14 minus the pOH. And we won't let the 14 factor into our sig figs. We'll let that be a round number. Minus 1.63. So what do you get out to the hundredths place when you do that? Should be about 12.37 or something like that. Is that about right?
Yeah, it's
Yeah.
12.3.
Okay. So it turns out to be a pretty basic value, doesn't it? And that's about what I'd expect, because what have I got? I do have a weak base that has a fairly small K value, but I've got a fairly high concentration of it. So I'd expect those two things to work together to give me a fairly high pH, and that's exactly what I got. Okay. So that's certainly a way to go about working that problem. The other way to do it is once I have the concentration of the hydroxide, remember I have that other relationship that comes from the KW, where it says the hydronium ion concentration times the hydroxide ion concentration equals KW. I could just solve that for hydronium. Once I got hydronium, I could then turn that into a pH by taking the negative log of it. Should get to the same answer. So there's a couple different ways you could have proceeded from there. Okay, guys, any questions about that? Everybody good?
Yep.
Okay. All right, so just a few other things I want to talk about. And then I'm going to try to sort of tie this into actually the experiment that we're going to do, or in the process of doing, I should say. And another one that kind of ties in here, it works from the point of view of letting you know something about material that's going to come up a little bit later in dynamics, but it actually ties in nicely to the standardization that you guys did last time. And it's polyprotic acids. Little did I know until I was starting to take some notes today that, oh yeah, this is a great example of that. Now, what's a polyprotic acid? Well, a polyprotic acid is any acid that has more than one acidic hydrogen. So in other words, it can donate more than one proton to a base, okay? A real common example of this, and the one that you'll see in pretty much any dynamics course, it's the one that I use, is H2CO3. That's carbonic acid, okay? So it's a fairly simple organic acid, if you will. Now, if you look at this thing, what's going to happen is carbonic acid can actually donate 2 of its hydrogens, okay? So here's the deal. We'll show both of them. HCO3, when it reacts with water, okay. This is going to be the acid, water is going to be the base. So you're going to end up making hydronium ion. And you're going to get bicarbonate ion. That's the conjugate base. Okay. Now, here's the question. Notice that the bicarbonate ion still has a hydrogen associated with it. That's still an acidic hydrogen. So what could happen here is that now the bicarbonate, HCO3 1 minus, could further react with water. So we'll now call that a Ka1, and we'll call this a Ka2 to make, again, hydronium ion. And now you get carbonate ion. Okay. Now, the interesting thing about this is that the Kas are actually fairly far apart in magnitude. The bigger one by far is the Ka1. So I went and looked them up. Ka1 is 4.46 times 10 to the minus 7th. And Ka2 turns out to be 4.69 times 10 to the minus 11th. Okay, so notice that there are several orders of magnitude, 7, 8, 9, 10, 11, what, 4 orders of magnitude between those things? And that's typical with these K values. Usually when you have a Ka1, Ka2, some even have Ka3s and Ka4s, there's generally going to be a fairly large difference between the subsequent Ka values, okay? So in other words, that first proton is going to be very easy to lose compared to the second proton. And if there was a third proton, that one would be a whole lot harder yet to lose, okay? So that's normally what happens. Now, when you get to dynamics and you start doing this there, okay, you can actually show, how you can subsequently lose these protons and watch what happens to the pH of the solution as you do that. But for us, I think the more interesting aspect of this is this. Let's focus in on the bicarbonate. Now, in this case, bicarbonate's a lot like, for example, something like water. Now, remember when we talked about water, we said water is kind of interesting because it can act as either an acid or a base. It can donate a proton, but it also is equipped to accept a proton. Okay, and you can see that here, right? If the bicarbonate ion donates another proton, that's your Ka2 reaction. But remember, this reaction can also go in reverse and the hydronium ion can protonate the bicarbonate to take it back to carbonic acid. Okay, so what I've got is a situation where this is called amphiprotic. And what amphiprotic means is that bicarbonate can act either as an acid or a base in solution, depending upon what it's in solution with. Okay, so let's just say I've got bicarbonate in water. Just an aqueous solution of it. Okay, so it's reacting with H2O. Okay, well, I've really got two possible ways this thing can go, right? I can let it be an acid, let water be the base. Okay, so what we end up getting is basically the Ka2 reaction, which we'll just write out again, where you get hydronium ion and you get the carbonate. And we know what Ka2 is, right? That's going to be some really tiny number. What do we say? 4.69 times 10 to the minus 11th. Well, let's look at the other option. What if bicarbonate acts like a base in water? Water acts like the acid. Put our L's down there to make sure we're good. Okay, so what do we get in that situation? Okay, HCO3 plus H2O. So what are we going to get? We're going to get hydroxide and carbonic acid. So now I'd have a conjugate acid and a conjugate base. Okay, so that's kind of like a KB, isn't it? That's kind of like a KB. Now, the question now becomes, okay, if I put carbonic acid in water, which way is it going to go? Is it going to act like an acid or is it going to act like a base? And how would I figure that out? What other piece of information do I need to be able to make a judgment on that?
Concentration of other ions in solution.
Okay, so yeah, concentration matters, but what other thing do I need a value of that would help me assess that?
KB.
Need a KB. That's exactly right. I need a KB. Oh, well, my table doesn't have KBs in it. So how am I going to determine that? How would I get a KB for this? Oh yeah, we remember that for any conjugate acid base pair, and that's what I got here, that Ka times Kb is equal to Kw, which is 1.0 times 10 to the minus 14th. So I want a Kb out of this. So my Kb is going to equal to my Kw divided by the Ka, just like we just did in the last problem. So that's 1.0 times 10 to the minus 14th. Oh, well, what Ka do I use?
I feel like you use Ka number 1.
Yeah, you sure do. You use Ka number 1. So it's going to be, it's the Ka for the original acid. Okay, so I want to use Ka1 down there for this. So that's your 4.46 times 10 to the minus 7th, right? And that's because I'm talking about a conjugate acid base pair. So when you look at this thing, the base is the HCO3 1 minus, the conjugate acid is the H2CO3. So the thing that would be acting like the acid in this case, from the point of view of those two things, has to be the H2CO3. It's the conjugate acid and the conjugate acid base pair. That's why I use the Ka1 there. Okay, so now if I work this out, that turns out to be 2.2 times 10 to the minus 8. So now, if I wanted to make a judgment about whether carbonate ion, or sorry, the bicarbonate ion, HCO3, is going to be an acid or a base in solution, I'm going to do it by comparing the Kb here to the Ka2. So the Ka2 says it's acting like an acid. The Kb says it's acting like a base. Which one's going to dominate here?
KB.
Yeah, so we definitely can say that Kb is going to be several orders of magnitude bigger than Ka2. So what we would expect is that bicarbonate will be a mild base in solution. All right. And that's exactly what we'd expect to see. So, at this point, what somebody could do there if they wanted to is you could go about and see, for example, whether or not that would generally be true. So if you wanted to, we could actually set this up like as an equilibrium problem and just see what the pH actually turns out to be. You guys want to do that? Set up just kind of a dummy problem here and see what happens?
Yeah, sure.
Sure.
Why not? So what initial concentration you want to use, like 10th molar or something like that?
Yeah, that works.
So let's figure out what the pH of 0.10 molar. We'll even be crazy. We'll put a counter ion in there. NaHCO3, sodium bicarbonate. Right? That's baking soda, isn't it? Sodium bicarbonate's baking soda. So in a case like this, the first thing we have to do is let the salt dissociate. So we'll show that in a step here. So I've got NaHCO3. Let it come apart into its ions. We know that happens 100% to the right because it's just a salt dissociating. It's a soluble salt. So I'm going to make sodium ion. And I'm going to make bicarbonate ion. Another thing we could ask ourselves, and you do this in dynamics, you should say, oh, well, I have two ions now. Do they have acid-base properties? And I kind of have to assess that, right? So the bicarbonate, we've already kind of figured out, is going to probably act like a base in solution. So we know it's going to be basic. Do you have any ideas on the sodium ion, what it might do? Acidic, basic, or neutral? Those are your options.
Neutral.
It's actually going to be neutral. And the reason why it's neutral is because it's the dissociation product of a strong base. And that strong base would be sodium hydroxide. Okay, so I always kind of go back to whatever the parent acid or base of the ion would be, right? So in this case, all right, sodium ion can't have a parent acid associated with it because the acid always has the H plus as the positive part. So if I see something like a metal ion, oh yeah, it's probably got to be the dissociation of a strong base, right? Like KOH or NaOH or aluminum hydroxide or one of those things. All right, and what do you know about the dissociation of NaOH? Well, that's a strong base, right? So it dissociates 100%. So if it dissociates 100% to the right, is there anything coming back to the left?
No.
No. So if there's nothing coming back to the left, you know that the ion is neutral. Okay, so that's kind of how you reason that out. And you'll do that a lot more when you hit your dynamics, when you get to acid-base chemistry there. So I'm just showing it to you here. You're going to see it a bunch more there. All right, so now what we can do is realize that sodium is really just a spectator ion. We don't have to worry about it. All right, so we get spectator ions out of there. We take the ion we care about. So that's the HCO3 1 minus. Let it react with water according to its Kb. All right, so what do we end up making? What's one product?
Bicarbonate.
Well, we're starting with bicarbonate. So what does it become?
Carbonic acid.
Carbonic acid. Okay, good. And what's the other product?
Hydroxide.
Hydroxide. You got it. Okay, good. All right, so I got an ice table now, right? I said I was 10th molar in bicarbonate. So water, we don't worry about. We haven't made any of that yet. We haven't made any of that yet. Reaction has to go to the right. So I've got minus x, x, and x. 0.10 minus x. Ice tables are like numbingly boring for acid-base reactions. They always look the same. All right, so what do we get? We get an x squared divided by, that should be a 0.10, sorry. 0.10 minus x, and that's all equal to, oh yeah, that KB we derived up higher. Where was that KB? Oh, there it is, 2.2 times 10 to the minus 8th. All right, so what can I do with that subtracted x?
Toss it.
Yeah, get rid of it. It's gone. Simplify the math. And this makes perfect sense because 10 to the minus 8th is absolutely tiny compared to 0.1. So I know I'm getting away with the 5% rule. I don't even have to calculate it. I know I'm good. So what does that give me? That gives me x squared is 0.1 times 2. So that's gives me what? 2.2 times 10 to the minus 9th when I multiply through by 0.1. Okay, so what does x turn out to be? I don't have a calculator on me. Put you guys to work.
4.69.
We'll call it 4.7 times 10 to the what? Or is that your, did you take that out? I just
Oh,
want
to the negative fifth.
10 to the minus, what was it?
Negative fifth.
Thank you. Now I got it. Okay. And what's that equal to? Oh yeah, that's equal to the hydroxide ion concentration from the ice table. Everybody see that? Oops. So I want a pH, right? So let's get a pOH like we did last time. That seems to be the way that most people prefer to do this. 4.7 times 10 to the minus 5th. What do you get?
Uh, 4.33.
Okay. And now the pH is going to equal to 14 minus the pOH, right? It's like we did in the prior example problems. So that's going to be 14 minus 4.33. So you're going to get like 9 and change, aren't you? Like 9.67 or something.
Yeah, 9.67.
Okay. So are we acidic, basic, or neutral?
Basic.
Or basic, yeah. And that's exactly what we would have predicted. So we've just proved that a 10th molar solution of sodium bicarbonate or baking soda is basic. Okay. And as a matter of fact, you know that works because anybody ever make the volcano where you add the baking soda to the vinegar?
Yep.
Yeah.
And put food coloring in there and all that? It's an acid-base reaction, right? So in this case, the bicarbonate is the base and the vinegar contains acetic acid. So that's the acid part. So you have a neutralization reaction happening there between an acid and a base. And what you're making is carbonic acid, which then actually decomposes into water and carbon dioxide. So that's what makes the bubbles. You learn something every day. All right, any questions about that, guys? So again, just more piddling around with acid-base equilibrium. So it's kind of a good thing to do. But sometimes you'll be in a situation where you'll see something like an anion of a weak acid. You got to ask yourself if it's got the option of either being protonated or protonating something else. You have to be able to predict which way that's going to go. So you do that by comparing a Ka and a Kb like we did in the case of the bicarbonate. Now, the reason I bring it up, and I wasn't even thinking about this until I was just scratching out some notes here just a little bit ago, is I was looking at, for example, the standardization reaction that we did last week. And that's with KHP. Okay. So KHP stands for potassium hydrogen phthalate, and that's a PTHALATE. And what we have here, and I've got to find this, so I actually scratched it out on the back of my paper here, is KHP looks like this. It has this formula. The K actually stands for the potassium, but it's C8H5O4. Okay, so I went and looked up actually what its chemical structure is. And this is what it looks like. You actually have a 6-membered carbon ring. This is what we refer to in organic as a benzene ring. So each one of those points there represents a carbon, and it has a hydrogen sticking out of it, except for here. Okay, what I have here is a C double bond O bonded to an O, and that carries a negative charge. And then you have the potassium counterion here to balance the charge. And then down here, you've got the same thing, only now this thing looks like a carboxylic acid. If I wanted to fill in my electron pairs, I could do that to make it a proper Lewis structure. And on each one of these is a hydrogen, just in case you wanted to know that. Okay, so that's what the actual structure of KHP looks like. Now, if you look at this thing, it's really kind of the same thing as bicarbonate, isn't it? Because if this thing comes apart in water, okay, what's going to happen is it's going to dissociate just like any other salt, right? So if I have that ring system there, which I'll just redraw, and a lot of times in organic chemistry, we show that conjugation of the double bonds just as a circle like that. So that's my shorthand way of drawing that ring. So now what I've got is a C double bond O bonded to an oxygen terminal with a charge on it, right? And then I've got this guy down here, which remains as a carboxylic acid. Now, do you see how this thing could have both a Ka and a Kb associated with it? So if it acts as an acid, what's going to happen? Well, I could lose that proton there. That's still an acidic hydrogen. So if this thing acts like an acid, I could lose that hydrogen ion. But how would it act like a base?
If it gains a hydrogen on the top negative part.
Yeah, so a hydrogen ion could come in and grab that electron pair right there. Okay, so this is what I would happen if the thing is acting like a base. And down here is what happens if the thing acts like an acid. So if it acts like a base, it's going to have a Kb associated with it. And if it acts like an acid, it's going to have a Ka associated with it, right? So I just happen to be looking at the structure and saying to myself, oh, that's interesting. It's amphiprotic, just like carbonic acid is. So now what we could ask ourselves is, if I just have an aqueous solution of KHP and I let it dissociate so that the potassium ion goes away, which way is it going to be? Is it going to be an acid or is it going to be a base? Okay, so what I did was I looked up a Ka for KHP. I just Googled it, and it's probably actually in your textbook, but I just Googled it, you know, like you guys do. 3.91 times 10 to the minus 6, if I can take that to the bank. Okay, that's for KHP. And really what KHP, when you dissociate it, is this. It's C8H5O4 1 minus, right? That's really what it is. All right, so now, could I calculate a Kb for it? Sure. Let's do it. So I know that Ka times Kb is Kw. So what that means is that Kb is going to equal to Kw divided by the Ka for the existing acid, okay? And actually, you know what? It would actually be for the fully acidic version of it, which I don't actually have a Ka for, but you know it's going to be bigger than 3.91 times 10 to the minus 6, right? So what would you expect to see there? Something big compared to the Ka or something small compared to the Ka?
Something smaller.
Yeah, so it's gonna be something a lot smaller than Ka. I didn't look up what the original Ka for this is. What I've actually got here for this is really a Ka2, but they just call it Ka. So it's going to be smaller than the original Ka that I looked up. Okay. So what does that tell me? Is KHP generally going to want to be an acid or a base in aqueous solution?
Base.
Is Ka bigger than Kb or smaller than Kb? Which is bigger, Ka or Kb? So another way of saying what I said there is that my Kb is going to be a lot smaller than my Ka, right?
You want it to be bigger than.
So yes, so this thing's actually going to be an acid because the Kb is not going to dominate. The Ka that I've got is going to dominate, okay? So should be acidic. And in fact, that's what it is. It's actually going to be an acid, okay? So let's just take a look at the reaction that we actually have in lab. What was reacting with what? Well, I had the K.
Sodium
Sorry.
hydroxide and
Yeah, so let's just break it down to a net
KHP.
ionic reaction. So I have C8H5O4 1 minus. That's my KHP after you lose the potassium. And it's reacting with hydroxide ion from the sodium hydroxide, right? So which is the acid and which is the base here, guys? That would make sense, right? If I got hydroxide in there, probably darn well better be an acid, right? Or sorry, a base. So what are the products of the reaction going to be? Well, the acid's going to protonate the base. So I'm going to make water. And I'm also going to make the C8H4. So I just lost a hydrogen there. So H5 became H4. O4. What is it now? 2 minus? All right. Now, here's the question. What's the K for that reaction going to be? How would I get a K? Is that like a Ka or a Kb? What kind of K is that? It's kind of weird, isn't it? Look at the reaction in reverse. Okay, so now the deprotonated KHP becomes the conjugate base. The water has to become the conjugate acid, right? So what's that in reverse?
it would be you'd be going after a KB.
Well, it looks a lot like a Ka. So if I reverse the reaction, let's just write it in reverse. So I think you guys will see it a little more easily that way. C8H4 O4 2 minus, which we said has to now be a base, reacting with water, which now has to be an acid. Okay. And what do we make? Well, we're going to end up making the C8H5O4 1 minus and the hydroxide ion. Now, if you look at it from that perspective, what does this look like?
It's got to be a KB.
It kind of looks a lot like a KB, doesn't it? Okay. That looks a lot like a KB. Now, what did we say above about KB? Well, we said it should be a really, really tiny value, didn't we? So in my original reaction, okay, if I wanted to define a K for that, it's the KB for the reverse reaction. Now, what do I do to a K if I reverse a reaction? Anybody remember?
You inverse it.
Yeah, I inverse it. So for that reaction, the K that I want, which I don't have a value for, is going to be 1 over the KB. Which is going to be 1 over a tiny number. So what is 1 over a tiny number?
A big number.
Really big number. It's a really huge number. Okay. So what does that really tell me about that top reaction up there? Is it going to favor reactant or product at equilibrium?
Product.
Yeah, so this reaction is going to go way, way to the right at equilibrium because it has a really big K associated with it because it's 1 over the KB of the conjugate base there. Okay, so as a result of that, what that's telling me is that for that reaction, as we run it, okay, do I need to really worry about any equilibrium?
No.
I don't really need to worry about an equilibrium. I'm going to more or less assume that that reaction is going to go stoichiometrically 100% to the right. So it's kind of like in the case of the KSP calculations and the formation of the precipitate that we did for the lab you're turning in tomorrow. What was the assumption we made about the formation of the precipitate? Well, that it was the 1 over the KSP, and the KSP was a really tiny number. So 1 over that has to be a huge number. So now it becomes what? A limiting reactant problem, right? So guess what? Our titration works the same way. In our standardization titration, we can assume just straight up stoichiometric relationships between the KHP and the sodium hydroxide because for all intents and purposes, the reaction's going 100% to the right. Okay, and we just showed that. Now I can go back and figure out what that KB is and prove it to you mathematically, but essentially that's what's going to happen. Okay. So what that boils down to, and it's kind of a long-winded way of showing it, is that whenever I have a weak acid reacting with a strong base, right? Because hydroxide is a strong base, a weak acid plus a strong base goes 100% to the right. Or even more generally speaking, we can say a weak thing plus a strong thing goes 100% to the right. So we don't have to worry about employing equilibrium. So I'm going to put my star up here, and that's where we'll call it for today. Weak component plus a strong component goes 100% to product. Okay? So no equilibrium is required in a case like that. So what we're going to find out is that we can basically just work it as a limiting reactant problem. Does that make sense?
Yep.
Okay, awesome. All right, so I think I've actually gone a minute or two beyond time here. So that's probably more than I intended to tell you, but I just kind of wanted to get to that point so we could talk a little bit about that reaction and why we were able to just basically treat it as a stoichiometric mole problem. That's why. All right, guys, come prepared tomorrow, and we will see you then.
All right. Thank you.
Have a good day.
You're welcome. You guys
Have a good one.
good
Thank you.
day.